Hello and welcome back. Let's continue with the arithmetic sequences. So we were looking at the properties of arithmetic sequences, and number 6 is relation between terms and indices. Again, this comes right from our golden rule. So if you look at different terms of the sequence, if you take two terms, if the sum of the indices are equal, then the sum of the terms are guaranteed to be equal. Okay? And you can prove it very simply. It's just a matter of writing down the equations for these terms AR, AS, AN, AM, and then show that this is true. So this is the condition. If this condition holds, the sum of indices are equal, the sum of the terms are also equal. If you think about the proof of the previous relation, you'll get some good results. In fact, this relation can be expressed more generally as below. And we can basically generalize that to three terms. If you take three terms and the sum of the indices are equal, then the sum of the terms in the sequence, in the arithmetic sequence, is also equal. Now if r plus s, these are integer numbers, is equal to n, then ar plus as equals 2an. If r plus s plus k equals 3n, then ar plus as plus ak is 3an. And the proof of these two come directly from the two above, right? So if in the previous one, r plus s equals n plus m, nobody said that m is different from n, so if I put m equal to n, then r plus s is equal to 2n, and the result is ar plus as equals an plus an, which results in 2an. Similarly, for this one, if r plus s plus k equals n plus n, which is 3n, then we immediately get this result. Okay, now the caution here is that if r plus s equals m, then it is not true that ar plus as equals am. Okay, and the key here is the first term. So if I really calculate ar plus as, is a1 plus r minus 1d plus a1 plus s minus 1d. If I calculate am, it's a1 plus m minus 1d, right? Now see what happens if we sum these two. It's 2a1, a1 plus r plus s minus 1d minus, and r plus m is equal to, r plus s is equal to m, right? So ar plus as equals a1 minus d plus am, and it is not equal to am, right? That's why this is not true, because if we expand both sides using the general term of a sequence, we can see that a1 is not eliminated from both sides, right? The left side has two terms of a1, so we had a1 here and a1 here, but the right side just had one term, which was here, right? Now let's solve this question, question 6. In an arithmetic sequence, the sum of fourth and eighth terms, so a4 plus a8 equal 14. What would be the result of adding up the fifth and sixth and seventh, a5, a6, a7? Now, first of all, these are consecutive terms, right? 5, 6, 7. And these are part of an arithmetic sequence. So immediately we know that the middle term is the average of the two, right? So a5 plus a7 is 2a6. So this is 3a6, right? I write it down. a5 plus a7 is 2a6. Now, 4 plus 8 is 12, right? So a4 4 plus 8 is equal to 6 plus 6. And therefore a4 plus a4 plus a8 should be 2a6. Basically a6 plus a6. So a6, we conclude that a6 is 7. And if we put it back here, 3 times 7, 21, right? So we get 21 as the result. Now, obviously, I mean, you can just use the general term and try to figure it out. But if you know this rule, if you understand this general rule of the sum of indices goes over the sum of the terms, but the number of indices, the terms should be equal. So if I have two terms, 4 and 8, it should be equal to two terms on the right side, 6 and 6. If I have three terms on the left, I have to have three terms on the right, right? So there's a strange property of these arithmetic sequences, and again, you can easily work it out in the terms that have the same distance. Let's say we have n terms in our sequence, right? And a1 and an have the same distance from the end. Basically, they are the first term, right? From the beginning, from the end. a2, an minus 1. a2 is the second term from the beginning. an minus 1 is the second term from the end. And similarly, a3 is the third term from the beginning. an minus 2 is the third term from the end. Now, the interesting thing is that we call these pairs a1, an, a2, and these are equidistant pairs. And by the exact property that we just discussed, the sum of their indices pair by pair, a1, an, a2, an minus 1, a3, an minus 2. The sum of the indices are all n plus 1, right? And because the sum of the indices of these pairs are the same, so the sum of the terms are also the same. Okay? Now suppose AR and AS are two terms of an arithmetic sequence. So do they have the same distance from both sides? Let's assume that R is less than S. Now, in order for these to have the same distance, these AR and AS must be a pair in the general pairs that we discussed, A1, AN, A2, NN minus 1. And the property of these equidistant pairs were that the index, the sum of index was n plus 1, right? So if I have AR, AS, and I want to make sure that the number of elements before AR is equal to the number of elements after AS, this is the distance, they have to be AR plus AS equals n plus 1, okay? Alright, now let's go to the sum or make a series out of these arithmetic sequences. And it turned out the sum also has a nice equation. So if let's say I have n terms in my sequence a1, a2 up to an, and I define another sequence Sn, and the sum over a sequence is we use the symbol sigma, capital sigma, of ak. K goes from 1 to n, right? So this n matches this n, so we have n terms in this sum, and usually we use S to denote a summation. Okay, summation. All right, so if I start from n equals 1, k from 1 to 1 is just one term, a1, and s2 is a1 plus a2, s3 is a1, a2, a3, and you sum them up. Now, obviously, it's very easy to see that Sn minus Sn minus 1 is equal to An, because Sn has A1, A2 up to An minus 1 n term. Sn minus 1 has A1, A2 all the way to An minus 1. And when you subtract this, you end up with An, okay? Now, if that relation is true, then very interestingly, what we can say is that, okay, let's say I want to find Sn, basically the sum of the first n terms of an arithmetic sequence, first n terms. And the way you can do that, a very interesting way, is like this. Okay, I want to find Sn, A1, A2 to An. But this is exactly the same if I write it backward. An minus 1 to A1, right? Now if I sum this up and use the equality, use the fact that these are the equidistant pairs, right? A1, An, A2, so 2San equal to, and these are basically n terms, n pairs, right? Let's write it n pairs. And they are all equal because they all have the property that sum of the indices is n plus 1. So n a1 plus an. Okay? So therefore Sn is n over 2 a1 plus an. And the way you remember is Sn is n, the number of terms, times the average of the first and the last term. This is the basic formula, the average of the first term and the last term. Okay, n times the average. And again, because this property holds true, instead of having first term and last term, you can say second term plus 1 from the end, any term basically. This is the important, right? As long as r plus s equals n plus 1. So let's solve this question to understand this property better. In an arithmetic sequence, the first term is a. If d is added by 1, how much will be added to the sum of the first 20 terms? Okay. So d is our constant progression, and we want to add d plus 1 to d, right? And then let's say we already, so let's say we have a sequence an that is made of a with d. And now we make a new sequence. The first term is a, but then d goes to d plus 1. And the question is S20 for b minus S20 of a. If I sum the first 20 terms of b and then the first 20 terms of a, how much is the difference? Okay, so S20 of b is 20 over 2 b1 plus b20. S20 of a is 20 over 2 a1 plus a20, right? So this is b basically 10 times. So our delta s is 10 times b1 minus a1 plus b20 minus a20, right? And b1 and a1, they are both a, so they are equal. And b20 minus a20, the first term is the same. It's just 19 times d of b minus d of a, which was 1. So this ends up to be 190. Okay? Question 9. The 10th term of an arithmetic sequence. So we have a sequence an. A10 is 39. And the sum of the first 8 terms, S8, is 136. What is the 16th term? So A16. Interesting. Alright, obviously what we need here is d. If I know what d is, I have all the properties of this arithmetic sequence, and I can solve it. Okay. Okay, so I can use S8. So S8, I know it's N8 over 2 times A1 plus A8, right? And also, so this is 136. So A1 plus, immediately I know that A1 plus A8 is this is a factor of 4. 136 divided by 4. 3 is 634. And then I know that A1 plus basically A10 is 39. Okay, from these two I can find A1 and D. Let's see. The way we do it is that A1 plus A8 is 2A1 plus 7D is equal to 34, and A10 is A1 plus 9D is equal to 39, right? And this is a linear system. It's very easy to solve. So if we want to solve this, multiply the second row by 2, and then 18D minus, and then subtract the first row. So 18 minus 7 is 11D is equals to 2 times 39 minus 34. Okay, therefore 11D is equal to 18. 2 3 78 minus 34 is 44, right? Therefore D is 4. And if D is 4, A1 is 39 minus 9 times 4, which is 36. So that's A1. And then A16 is A1 plus 15D, which is 63. Okay, so 3 is correct. All right, this was the arithmetic sequence that we had a constant progression. Each term was the previous term plus a constant. Now we go to a geometric sequence. In the geometric sequence, each term is the previous term multiplied by a constant. So consider a constant number A1 and a constant number R, which is not 0, and plus minus 1. Let's assume that it's also plus. Basically, the magnitude or the modulus of R is not 0 and 1. Because if it's 0, we multiply it, we only get 0, 0, 0. If it's 1, we get the same thing. So it's not a meaningful sequence. And now we make a sequence such that the first term is A1, and each next term is obtained by multiplying R to the previous term. This sequence is called geometric sequence. It's very important. This is a very important sequence in math. R is called the common ratio. Has different names. Let's call it common ratio. And if you look at the general form, so general form of sequence with n terms, A1, A2, A3 to AN, and A1 is A1. We form A2 by multiplying A1 by R. Now instead of adding, we're multiplying. A3 multiplying A2 by R, so it becomes A1R squared. And we continue this multiplication, so AN becomes A1 times R to the n minus 1 power. Now compare this with the arithmetic. AN was A1 plus n minus 1D. I mean, there are some similarities. So n minus 1 appears again, but now instead of a linear thing, it's power, R to the n minus 1. Given the sequence 1, 3, 9, 27, prove that this is a geometric sequence. Okay, let's see. 1 multiplied by 3, 3 multiplied by 3, 9 multiplied by 3, and again. So yes, uh, this is a geometric sequence. A1 is 1. The common ratio, common factor, or the multiplication factor is 3. Find the general term. An is a1, which is r, which is 1, r to the n minus 1, 3 to the n minus 1. Find the 10th term, so a10 is 3 to the power of 9. Okay? Properties of geometric sequences. Now, obviously, by definition, each term divided by its previous term should be constant, and all these ratios should be equal. A2 over A1, A3 over A2. This is by definition. This is a property that comes right out of the definition, right? Now, just like the arithmetic sequence that we had 3 terms and there was a relation between them, here for the geometric sequence we also have a relation. Now, if A is some term, B is the next term, and C is the next term, we have to multiply by R, right? So B over A, B should be A times A times R, and C should be B times R, which is A times R squared. Now, the very important thing now becomes that B squared is A times C. This is important. Now, in arithmetic sequences, we had 2B A plus C. Now, you see the similarities here. 2 goes to the power and sum becomes multiplication. This is generally true. The analogy between arithmetic and geometric series, right? And this becomes times. A geometric sequence can be presented in any of the following ways. Exactly the discussion, similar to discussion we had in arithmetic sequences. So A multiplied by R, so AR squared. A over R, so that when you multiply by R, it's A, and then multiply by R, AR. A, B, C, in order for them to be consecutive terms in a geometric sequence, B squared should be A times C. Now, if you remember, we solved this for arithmetic sequence. If you have a right triangle and they were the terms of a arithmetic sequence, we found out the results was 3D, 4D, 5D, right? And now let's see what happens if we assume that A, B, C are terms of a geometric sequence. Now again, we have A squared is B squared plus C squared. So assume that the R is greater than 1. So A should be the largest term. And let's say B the smallest one. Smallest. Okay? So C becomes B times R, and A becomes BR squared. And you put them in Pythagorean, you end up with R4 equals 1 plus R squared. Now we'll get to solving these equations, but the solution then becomes R4 minus R squared equals 1. And then we make it a complete square. R minus 1 over 2 squared is 5 over 4. Therefore, R squared is 1 plus square root of 5 over 2. And therefore, R is square root of 1 plus square root of 5 over 2. It's a little bit a scary number, but yeah, that's R. Alright, putting geometric sequence between A and B. This is the same, this is exactly the same thing that we had for arithmetic sequences too. So we can, let's say if we have A and B and we want to put K numbers in between A and B so that the whole sequence forms a geometric sequence. Geometric sequence, right? Now the question is, what is the relation between K, A, B, and the common ratio R, right? That factor that we use. Obviously, if you have weak k terms and this is geometric sequence, by definition, a becomes term 1 and b becomes term k plus 2, right? So b becomes the k plus 2 terms, and if you use the general relation is a times r to the k plus 2 minus 1. So r to the k plus 1 is equal to b over a, right? So basically r is b over a raised to the 1 plus k plus 1 power. And again, we get to the power functions and how to calculate these.